Hi, welcome to this talk. Title of this talk is C, Crypto, and Clojure. I know the one that it says on the schedule is a little bit different, but this is about combining Clojure with native libraries. So I'll make sure to put the link of this, for the slides up later, just in case you want to peruse them afterwards. So a brief introduction. Hi, I'm LVH. I'm a cryptographer, and I do distributed systems and cryptography and generic information security work. I work at a company called Latticora. We do security programs for startups. So if you're a startup and you would like to do something around security, but you're not really sure where to start, you should come talk to us. And so as I said, the title of this talk is C, Crypto, and Clojure. The subtitle is with sparkles. That's the Unicode symbol of sparkles. It'll become clear by the end of the talk why that is. So why Clojure? Just to deconstruct that title a little bit. I love Clojure. It's my favorite programming language. I'm guessing that's not going to be a very hard sell since I'm at ClojureConf. But just for the people who are watching this later recorded, Clojure is great. You should try it. But the other thing that's kind of interesting is the thing that I've been doing with Clojure. I've been doing a lot of stuff with Clojure, mostly in the security space. But one of the things that I've been doing is cryptographic research. And that's interesting because usually cryptographic research is something that's limited for languages like C, and very often even like C with like assembly shivved into it. Rarely, depending on what people are doing, maybe even some Go or some Rust. But by and large, it's a systems programming language field. And Clojure, like certainly not a hosted programming language, certainly not one on the JVM, and generally speaking, not Lisps, are not well known for being useful programming languages for doing that in. So why crypto? Well, I already mentioned I'm a cryptographer, so that's what I do. The phrase, don't re-implement your own crypto, is thrown around a lot, and it seems to mean something else to everyone. And in my case, it means a couple of things. So one of them, for example, if there's a perfectly good working implementation of an algorithm, it's not necessarily interesting for me to go and re-implement that. Just because I'm lazy and I don't necessarily want to do rework, but also in many cases it turns out that it's essentially impossible to do the exact same thing that you would be able to do natively to do that in software. So two examples of that, for example, are PCL-MOL-QDQ and ASNI. So PCL-MOL-QDQ is an instruction on modern Intel CPUs. ASNI is an instruction set on modern Intel CPUs. And these are used to implement portions of cryptographic algorithms. So if you're familiar with, for example, AES-GCM, if you've ever configured TLS, you might have seen that string pop up somewhere. PCL-MOL-QDQ is used for that. The thing is, you can do that technically in software, and you can implement it correctly in the sense that for every input you get the correct answer. But that doesn't mean correct in the cryptographic sense, which has stronger requirements. For example, to be correct in the cryptographic sense, it has to, for any input, take the exact same amount of time. And that, for example, is extremely difficult to do in software. So there are good reasons why you want native CPU instructions instead of just re-implementing the same algorithm in software. So why C? Well, to be entirely honest, it's more about the alliteration than anything. It's really about the OS ABI, or the application binary interface, or quote-unquote native code, rather than C specifically. It just turns out that C is kind of the lingua franca for doing this. Even if the code that you're calling is secretly implemented in Fortran, the way that you're calling it is going to be a C-style way of calling it. So in order to answer that question, it might be interesting to ask the converse question instead, which is why would you want to limit yourself only to the JVM and Clojure? And I'm not trying to be cheeky when I ask that. There are perfectly good reasons for wanting to keep all of your code on just the JVM. It makes your code really easy to send to some new platform, for example. There are also really good reasons to just keep your code in Clojure. I've had plenty of code that I originally wrote targeting the JVM, and I renamed the file from CLJ to CLJC, and 2 minutes later it was running in my browser, and that's awesome. And you give that up when you use native code. That said, there are really good reasons to use native libraries. Performance can be one of them. Very often these C implementations, or I mentioned Fortran, these things are pretty fast. But it's not really just about performance. So I already mentioned, I'm not going to re-implement stuff for fun. If you want a large amount of linear algebra algorithms, those things have been written in Fortran since the 70s, and they're collected in excellent libraries, and there's absolutely no point in re-implementing them. But there are all sorts of other things. So I mentioned crypto. You might care about OS features. So if you want interactive process control, you don't really get the same amount of power that you get on the JVM as you do if you were a native program. That might include like network sockets, high performance I/O, native GUI features. If you want to do math on the GPU, those are all things that you might want to do from a Clojure program and that you can't do by just sticking to the JVM. You need to go drop down into a native level to accomplish them. Sorry, that was the wrong slide. Oh, no, there we go. So let's call some native code. How do I do that on the JVM, generally speaking? So historically, there was JNI. And JNI has been in Java for pretty much forever. And what happens is you have your Java code, and it makes a JNI call. And I'll show you what that looks like in a second. And then it runs over into C country, which is a long and arduous process, which is why it's a squiggly line. And then in the second line, you're in C country. You can tell because everything is monospaced, and you no longer get nice Unicode aeroglyphs. And it calls a JNI implementation, which is a C stub. And then eventually you call your library. So what does that look like when you actually try to do it? So here I'm trying to bind getpid, which seems like a simple thing that you want to call. Like if you're familiar with doing programming on like standard C or even like Python or Ruby, like getpid is something that's around, and getpid is something that's very useful. If you want to start a subprocess on POSIX, you need to be able to call getpid. And yet, the JVM, to my knowledge, still doesn't expose this because mostly just compatibility reasons, because not necessarily every place where you run a JVM, you also have a concept of a process ID. So the interesting thing here is, and I try to highlight it, is that native keyword in Java. So that makes this a JNI call. And then I call getpid. I need to statically tell it to load a particular library that is going to have getpid in it. So that's actually a JNI library. I'll show what that looks like in a second. It says dilib because I'm on macOS. If I was on Windows, that would say DLL. If I was on any of like Linux or BSD, that would say SO. And then you call a thing called Java H, which is Java C's weird brother. It comes with your JDK, so it's probably already installed on your machine. And it just generates this weird C header file. And the point is not to, like, as you can see, it doesn't even actually fit on the entire slide. That's kind of the point. What I'm trying to demonstrate is, like, this is gnarly boilerplate code. This is the simplest C call that I could think of, and it's already looking kind of gross. And then that's just the C bridge. Then we still haven't actually called getpid. So you still need to require that or include that header and then actually call getpid. And as you can see, like, this doesn't even really look like, it's very, very specific code. Like, you have that JNI call in there. Like, who knows what that does? You have a JNI end pointer, which is for calling back into the JVM. Like, this is very specific knowledge. It's not easy or fun, and it doesn't really look like you're calling C code. You're doing JNI, and there's a difference. So, and then eventually, of course, now you just have source code, right? You still don't actually have a working getpid call. So then you need to invoke your toolchain in order to eventually produce that SO that your JVM will be running at runtime. So your toolchain barfs some eldritch runes at you, and then maybe eventually you're able to call getpid. And I found an example of this in the wild. So I mentioned that one of the things you might want to do is GPU math. And there's a really cool Clojure library for doing that called Neanderthal. Neanderthal depends on a library by the same author called OpenCL, and that finally depends on a Java library that I can only imagine is pronounced Jockle. And if you go reach into the dark ichor heart of Jockle, then eventually you see a native keyword in there. So there is absolutely production Clojure software out there that uses JNI right now. That is, well, it does it through Java, but still. So the problem with all of this, or rather the upside, like, you can use Neanderthal. It's fine. You could just add the dependency to project CLJ, and it works great. So JNI, it's also really performant. JNI is great as long as you can get someone else to do the compile bit for you. But if you're in this talk, then I'm guessing that you're possibly interested in binding your own native libraries, and that means that you're the sucker who has to go do the compile bit, right? So this was generally accepted as a problem with JNI. And as a consequence, in days of yore, Sun came up with JNA, which is the same but different. So one of the differences, for example, is that there's no more native keyword. You specify the things that you want to call by implementing an interface. And then just at runtime, you can try to load a library. Typically, you'd have to specify the name of the library. In this case, I don't, because getpid is in libc. And then you can call getpid. And you don't have to run a compiler. You don't have to, like, generate gnarly header files. Like, this is pretty good. Unfortunately, there's some problems with JNA as well. So the biggest one by far is performance. So I've heard anywhere between, like, 1 order of magnitude and 3 orders of magnitude, like, cost for doing JNA versus the JNI implementation. maybe that's fine. Maybe you have like some really, really long, maybe it's either not performance sensitive or the C call that you're doing is really, really expensive such that the overhead like doesn't really matter. That's not really the important part. But still, it's not perfect. There's also some missing features that you probably care about if you're going to bind any meaningful large C library. So enter JNR. So how JNR works is, this probably reminds you of the JNI slide, but you have your code, which calls a JVM-generated stub. So this is still JVM code. We're on top here, right? And then that makes a JNI call. The JNI call goes over into C country. There's a JNI C bit there. That calls a library called libify, and libify calls your library for you. Now, I would understand if you're confused or incredulous at this point, because I just told you that JNI is annoying and JNA is slow, and somehow the answer is like JNI, but with more overhead. You'd be right, maybe. But it turns out that it's a little bit better than that. So first of all, that JNI platform-specific bit that I talked about, so that would be the actual JNI call, that just has to link to libify. Libify is going to be the same everywhere. So the annoying compiled bit is going to be shared for everyone, or pretty much everyone. Like, it probably ships with support for your platform. Because that part is shared, what that means is there's still a sucker who has to do the JNI compilation bit, but it's somebody else now, so that's OK. The JNR specific part is generated at runtime, so you get the same behavior that you would out of JNA. So it would be more fair to say that you get the JNA user experience, roughly, with the performance of JNI, roughly. I'll go into performance more in detail afterwards, but they're roughly the same. So what does that look like? Like I said, it's very much the JNA experience. So you create an interface that defines the methods that you want to expose. There are some annotations here. I'll go into more detail about what those do later. In order to demonstrate some of the features of JNR FFI, I'm calling a slightly more complicated C function now. It's not particularly complicated, but get time of day just tells you what time it is right now. And get time of day takes a time val, which is a struct that it's going to put some data in, and a pointer, which is normally for time zone, but here it's unused. So the JVM or JNR doesn't define what time val is. So sometimes if you have a struct in C, you still need to tell JNR, like, hey, here's what that struct looks like. It has some seconds, it has some microseconds, and you're off to the races. We have JRuby to thank for this. And the reason we have JRuby to thank for this is because JRuby tried to mimic an existing Ruby implementation, MRI, which is a C program. And MRI was written to do whatever it is that C programs can do, right? They're going to do all their fancy terminal manipulation and socket I/O and yada, 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 because they're not really worried about the difficulties that someone is going to have 10 years from now when they try and implement it on a hosted platform like the JVM. And JRuby kind of said from the start, we're going to be just like Ruby, except just faster and with better concurrency. And as a consequence, it was unacceptable to say, well, OK, we're just like Ruby, except like 90% of Ruby programs don't actually work. So they needed to implement a whole bunch of features, including all sorts of file system access things that the JVM doesn't provide, interactive subprocess interaction, which you can't really do as well on JVM. I mentioned terminal control, and also fast I/O. Because of course, if your claim to fame is like Ruby but faster, and then it turns out that all your I/O calls are slow, and also turns out that most Ruby programs are I/O bound, then well. And also off the shelf, they provide a whole bunch of stuff. So I'm very thankful that they didn't choose to implement all of this simply in JRuby. They wrote individual libraries that then JRuby depends upon. So for example, I talked about get time of day and get PID. You don't actually need to bind get PID or get time of day because they provide you with a library called JNR POSIX that does all of that. I'm told that they also expose fork. And when you fork the JVM, it like breaks comically. But whatever, you can call it if you'd like. There's also JNR Anxio, which is basically really performant native I/O. I think that Neo didn't exist when they started with that, but it turns out that even with an I/O, with the new I/O system in Java, both Netty and JRuby like kind of discovered this independently. If you can do it with native native calls, you still end up being faster than the JVM specific things. And then JNR Unix socket, just in case you want to talk to a Unix domain socket for reasons unknown. There's also a bunch of tooling that they provide. So JNR constants, if you have a C library and it exposes preprocessor constants, so they're not going to be visible in the C code that gets passed to the compiler, that's an awful lot of libraries. Very often, you don't want to just insert the magic number 2. You want to know what that constant means. JNR gives you really good tools for being able to access those. There's also JNR x86 ASM, so that lets you shiv some assembly in the middle of your Clojure code, because who doesn't want to do that? That is also how the stubs are generated. So they generate their stubs at runtime very often by literally generating assembly. OK, so let's go write some code. The easiest way to get started is with Java, because that's what all of these samples do. So if you look at the documentation, all of this code assumes that you're writing Java. So let's start with some Java. The library in particular that I wrote and that I'm using as a guide for this talk is a library called Cesium, which is a Clojure binding on top of libsodium. Libsodium is a cryptography library. If you're familiar with Dan Bernstein's NACL, or allegedly pronounced salt, but that's not going to happen. So NACL, it's NACL with cheese. And by NACL with cheese, I mean it's in version control, it's buildable, you can probably get a binary for it for your platform, and they added a couple of features here and there. So how much Java do I need to bind? Just to get an idea, I got a checkout of libsodium, and I counted the number of header lines. And it turns out that there's like north of 9,000 header lines. I wasn't very happy about that, but OK. I can do that. Fortunately, it's mostly easy Java, because libsodium has a very consistent API that's explicitly designed to be easy to call from a whole host of different languages. So Clojure is absolutely by no means the first language that someone bound libsodium in. There's plenty of other languages, and it was explicitly designed to make that as easy as possible. So most of it's char*, which is a pointer to, char*. Now, the problem with that is that there's actually a lot of JVM types that you could use to represent a char*. There's the concept of a sequence of bytes. There's not one unambiguous Java type that you could use for that. So in JNR alone, there's for example, there's a pointer type, which is explicitly, char* is a pointer. There's also buffers and byte buffers just in Java. There's also string, because sometimes the thing that the char* is actually human text, and you want to use a string for that. And there's also the built-in primitive, a byte array. And even then, you're not really done, because what do you do in order to pick the return type of a function, right? So I can either give you a function for each one. So I can say, like, hey, if you want a buffer, call this function. If you want an array back, then you call this other function. Or I could try and be really clever and look at the things that you gave me and assume that you want something back that looks kind of the same shape. I tried that at first. It didn't really work out really well, because there's a bunch of functions that take, for example, 4 or 5 arguments. And if you give me 5 different types or 4 different types, then I don't really know what you want, which one you wanted. And then it's still kind of annoying to have 2 functions for every semantic function. And then the other thing is, do you want a functional interface or a mutate in place interface? I'm a functional programmer. I would prefer the functional interface most of the time. But none of those types that I just mentioned that you can reasonably describe some bytes with on the JVM, none of those are I was going to say value types, but none of those are values in the sense that they're immutable. The other problem is there are very good reasons for wanting to bit bang in place a particular array. Like if you don't, for example, if you don't want your key to be copied over memory all over the place, or if you want, for efficiency reasons, you want to be able to use the same buffer again and again, then there are good reasons for wanting the in-place API. And then in order to get to the right types, given this idea that, oh, there are a bunch of types and you might have whatever and I need to be able to use them as much as possible because I want my library to be user-friendly, there's a whole bunch of options and all of them are kind of bad. Because I might want to try and do conversions, but very often that means that I'll need to copy because a lot of these types are not intercompatible. If I do reflection, typically it's going to be slow. There's a performance penalty for that, and it turns out that it's buggy. I found, well, arguably buggy. I'm still not sure if it's a bug or a missing feature, but I found a bug in Clojure's reflector where it was unable to find a method that I knew existed on that object. If I do explicit methods, because there's this combinatorial explosion, if I do explicit dispatch on the type, first of all, it doesn't actually work most of the time because there's hidden types that the JVM will give you back, so you can't actually just check the type and then do static dispatch. You actually need the reflection. But the other problem is that because there's so many options, you're going to get a very, very large type. And if you have any experience with JVM performance optimization and writing high-performance code, then you'll probably have heard before the heuristic number one is write smaller methods. Because it's quite possible that even though Hotspot, the JIT, will look at your method and be able to optimize the living daylights out of it, in reality, it's not even going to try because it's too big. And if I tell you, like, well, tough luck, this library uses byte buffers, deal with it, then that makes my library a lot harder to use, and I would like to be friendly to my users. So as I mentioned, very quickly you end up with this combinatorial explosion of symbols, right? Because for every return type you have an option for functional versus in place, and then all of the possible permutations. So very quickly, before you know it, I'm exposing, I think I did the math on this once, I ended up with 12,000 symbols, which wasn't going to happen. So I needed to pare that down a little bit. Unfortunately, there's a couple of good places to start. So first of all, pointer is really just useful if you're going to be essentially not really reading a piece of data from JVM land. You just need to pass it to a C function, and then pass it to another C function, and pass it to another C function, and sort of down the line that way. So a pointer is very opaque. And if you're OK with that, pointer's fine. But I don't want opaque types. I want to be able to read those bytes. The other thing is strings are straight out. As I already mentioned, strings are typically for human text, right? They're sequences of Unicode code points. And I have no idea if the thing that you're encrypting that might be human text. It could be an image. It could be some binary data format. It could be compressed. It could be all sorts of stuff. But generally speaking, encryption algorithms work on bytes to bytes. They don't work on Unicode code points to anything else. So that leaves us with byte arrays and byte buffers. So byte arrays are nice because they're really common. They've been in Java pretty much forever, and they're very easy to use, for example, in serializers. So if you have like a serializer library, it probably already knows what a byte array is. On the other hand, byte buffer is newer, but it does have some distinct advantages. For example, it's the only reasonably supported way on the JVM to get directly allocated memory. So if you want some memory that's off the Java heap, you want it to be as if you just called malloc in your C program, then you call bytebuffer.allocateDirect, and that's the only way you can do that. The other nice thing is if you have like a binary format and you need to read the first 2 bytes because that's the header, and then you need to read a byte because that tells you how many bytes are following, like Pascal-style strings, then byte buffers let you do that very easily. So it's very cheap to create like a slice in memory and just go look at that 1 byte, or go look at this sequence of bytes. And if you do that with byte arrays, it's a little bit annoying. Very often you need to copy stuff around. There's some asymmetry there as well. So if you have a byte array, you can wrap it with a byte buffer in order to do that view thing. And that's really fast. As far as I know, going from an indirect byte buffer, which is to say a byte buffer typically backed by a byte array, getting that byte array back out is also really easy because that's just field access. My reading of the documentation says that this isn't really guaranteed. It just turns out that it works that way on every platform that I've tried. But then the problem direct byte buffer, which is the one where you really, really, really want a byte buffer because it's the only supported way of doing it, if you want to go from there to a byte array, that's really slow because every time you cross that boundary, you have to copy everything. Because a byte array definitionally lives on the Java heap, and the direct byte buffer definitionally does not. So one of them is going to have to budge. So the way that I solve this, in conclusion, is first of all, I wanted to expose everything on the underlying object. I wanted to make sure that if you knew exactly what types you had, you could just go call the right thing and pay as little performance overhead if you wanted to. So you have to opt in into doing some gnarly stuff and maybe do some type annotations and stuff like that, but at least you can if you wanted to. The in-place API takes buffers only, because the in-place API, it turns out that if you wanted something in a byte array, it's easy to wrap, so that's OK. And in the cases where you really, really want to make sure that you're going to the specific location in memory, you have a direct byte buffer, so you have a byte buffer, so I want to make sure that that API takes byte buffers. And then there's the high-level functional API, where I try and be as flexible as possible about what you give me. I make sure that I wrap it. Turns out that's always, or usually, efficient, because either you already have a byte buffer, or you don't, but then I can wrap it, and it's still efficient. And then eventually you get a byte array back, because you don't care where it's stored. If you cared where it's stored, you'd be calling the other API. So that was a little tricky to figure out. That took a couple of days of hammock time, as Rich puts it. But eventually we got there. So performance. Which is, in many cases, like I said when I started the talk, there are many reasons to do this that aren't about performance. But generally speaking, performance isn't a bad one. There's nothing wrong with making your program run fast. And the short version, if you remember anything, is the penalty is really small. Like, it's fine. It's extremely unlikely that you have to care. There are knobs that you can twiddle if you really want to make it very, very, very small. And when I say very small, I mean like order of magnitude 2 x86 instructions that are reasonably branch predictor friendly, so fast. And it turns out that the JVM tooling for this is pretty good. So for example, there's a thing called JITwatch built by the OpenJDK people. It tends to focus on Java, but because it deals with the hotspot JIT, it doesn't actually really care about Java, so you can use it with Clojure just fine. You just end up getting the mangled names instead of the Clojure namespaces that you might expect. And you can even get assembly dumps out of the JVM. So you pass these weird command line flags, and you can set it a bunch of other ways, but then you end up getting assembly. And you run that, and then it tells you, OK, print assembly is enabled, and you go run your entire program, and you're expecting to see some assembly, and eventually you're confused because it's not going to standard out. It's not like writing a file. You end up S-tracing that process. Turns out that you can't S-trace it because on Mac OS now, it's protected from being, Java by default, the JVM is protected from being S-traced, so that doesn't really work, and you end up spending a bunch of time. And eventually you decide that maybe it might just be a good idea to read the rest of the output of that program, and it tells you, oh, I couldn't actually find this really critical library, so when I told you it was enabled, what I actually meant was that it was disabled. So then you acquire HSDIS, which requires getting a checkout of OpenJDK. You need to build your own bin utils. There's extensive cursing there. But eventually you acquire that dilib. You can do this. It's OK. It's annoying, and it's a little bit roundabout, and you need to like manually do some stuff. But eventually you acquire this. So for those of you who have never seen an assembly output, I'm sorry. But for those of you who have, this should look kind of familiar. So this is what happens when you try to call count on a seek. So for those of you who are familiar with assembly, or maybe remember it from a very far away college class. So here I'm, well, I'm not. The JVM is pushing the base of the stack, and then subtracting the stack point 30 from the stack pointer, or 0x30, and conveniently HSDIS will tell you what is there. So it will tell you what it's exactly accessing. And then there's a NOP, because of course C is odd, and I don't know, Intel CPUs are weird, so you only want instructions on even addresses. And eventually you call something. It of course tells you what you're calling. You can see that this is invoke virtual, which is a JVM bytecode instruction. You're calling count. You're calling count on async, yada yada yada, and eventually it restores the stack pointer and restores RVP. So if you're reasonably familiar, if you've ever done any x86 assembly, this will probably look pretty familiar. If it doesn't, I'm sorry. But now the nice thing about this is, like, this is obviously a pretty simple call. This is pretty much the simplest call I could think of. I couldn't show the crypto ones on the slide because that would not fit on the slide. But the nice thing is, regardless of what your code is, what you can now do, and I've actually done this exercise for my crypto code, you write a C program that does the thing that you expected your Clojure code to do. And you run HSDIS on your Clojure code. You see what the produced assembly is. You get clang-03 to produce a C binary that allegedly does the same thing. And then you see that you can very concretely, in terms of numbers of instructions, which in the crypto community we care about, in terms of numbers of instructions, you can see exactly what the penalty is of using Clojure. And it turns out that the answer is very, very little indeed. JNR has a number of tricks. Check what time it is. The JNR has a number of tricks, mostly in the form of annotations. You saw them perhaps in an earlier slide, in order to make this a little bit faster. So one of them, for example, is ignore error. If you've ever written any C code, you might be familiar with the concept of errno. So because C doesn't really have a decent error handling mechanism, sorry, that was a value judgment, but I'm going to repeat it. Because C doesn't have a decent error mechanism, what ends up happening is a function will return a value that tells you something went wrong, and then you need to go reach into errno in order to figure out what exactly went wrong, and then you do your error handling based on that. Now, the thing is that the JVM internally uses errno. So when you call some C code, that's allowed to do whatever, including use errno. So by default, if you call some C code, the JVM needs to save the errno value, and then when it returns, it needs to check the errno value, it needs to allocate a threat local, it needs to put the errno value back, because otherwise the JVM breaks. Now, a lot of C code does not use errno, and if you incidentally know that that's the case, then you can tell JNR, hey, I don't care about errno, just forget about errno, you don't need to do the save and restore thing, and that lets you shave off a few cycles. There's also annotations for in and out. So normally what happens is when you call some C code, you have to keep in mind the value that you're calling it with is managed by the JVM, right? So it could be an object, it could be a primitive, but it's managed by the JVM. So it lives in JVM memory land. And in order for some C code to call it, you need to copy it first, because the JVM reserves the right to copy stuff around, and it does that all the time for purposes of garbage collection. So you can't just like pass a pointer around and expect that to work. So it needs to copy it back, and then copy it into C country, call the C function, and then copy it back into JVM country when the C call has completed. Very often, though, C code will have certain parameters as either an input parameter or an output parameter, by which I mean you're passing it like a pointer to an int or something, and that function's contract is, I will put the result of my computation in the location of that pointer that you gave me. And when you know that's the case, for example, if it's an output parameter, there's no point in copying whatever the JVM had into C land, because most of the time it's going to be like all nulled out anyway. So there's no point, because nothing will be reading that. And conversely, if it's an input parameter, if you know that you're just passing it to C, but you're not, you don't need to copy it back, because you know that the contract of the C code is, I'm not going to change this value, I'm just going to read it. So in order to optimize that, you can you can set these things saying that this is only an input parameter or only an output parameter. Again, this is opt-in, right? Like if you just bind your code really quickly and it turns out to work fine and it's fast enough, then don't bother. But if you really want to and you really care about those those two x86 cycles or instructions or whatever, then you can absolutely do this kind of thing. I just said, hey, the JVM reserves the right to copy stuff around, and therefore you can't just pass a pointer. That was a lie. You can absolutely do that. You just have to tell the JVM first. So JNR has this really cool feature called pinned, where you essentially tell the JVM, hey, you know that part where you thought you owned that region of memory? You don't. Just don't touch it for a while. Just trust me. And instead, that means that you can just pass that pointer along, and you can just pass that pointer to C. C country is going to do something at that memory location, which is secretly still managed by the JVM, except the JVM has promised to keep its hands off it for a while. And then by the time it returns, you're done. And that means that you don't have to copy anything, like you're done. So that's terrifying. Think about that for a second. But still, though, if you were to be passing a struct, so I gave the example of doing get time of day. And get time of day, you pass a structure around that has a number of seconds and a number of microseconds. And if you're doing that, then the JVM needs to allocate some memory in order to copy that struct into. Now the question is it necessary to keep that memory around? Because it's possible that you just, by default, for example, you just copy something into C country, C function does its thing, and then you copy it back. And after that, you could free that memory because it's not being used anymore. It might be interesting to make sure that you use that same location in memory the entire time. Could be that your C library requires it. Could be that you don't want to call malloc very often, stuff like that. And direct and transient let you tweak that behavior as well. And again, just to repeat, all of this is opt-in. Unless your C library, for example, like if your C library does something really silly, then maybe you need this for correctness. But generally speaking, all of this is opt-in. You only do this because you want to squeeze the maximum amount of performance out, which you might not care about. Now, everything that I've talked about so far, and I want to make sure that I have enough time, I think I do, is about Java and the JVM. And the kind of crux of this talk was, but Clojure is really good at it too. Why is that? Well, so my library Cesium has no Java whatsoever. And that's mostly just because I didn't want to write any. And it turns out that's one of the decisions that I made all the way at the beginning. And that turns out to have worked really well. So first of all, Clojure has really good host interop, right? This isn't really a secret. Clojure doesn't hide Java or the JVM from you. If you really want to, you can write essentially Java just with more parens. For example, we mentioned you need to define an interface, as in a Java interface, a JVM interface, to define what kind of things you're going to be calling on your C library. And Clojure gives you a thing called def interface, and you can just define get time of day that way, and this is not particularly surprising or confusing. The only thing about this maybe, so if you've never seen this create int, that's just a type hint. So this will say, hey, get time of day is going to return an integer, and I pass it one argument, which is a time value, or a time val here, and I pass it another argument, which is a pointer. The only thing that might be really new to people who have done type hinting before is that thing, and that was not easy to find. That is how you do annotations in Clojure. So you can do that on def class, you can do that on def interface. That seems to be tribal knowledge. But if you only take that away from this talk, hey, win, right? Now, I'm not quite as well-spoken as Rich is, but my understanding from some of his earlier talks is that the Clojure way can roughly be summarized as start by having some data and then don't mess it up. And that's kind of what I did. So I have some data. So specifically, this is a thing from this is an excerpt from Cesium. This is just a vector. And it is a vector that has the same shape as def interface for a good reason, because I'm going to use a macro to shiv it in there. But it is just a data structure with some vectors and some maps in there. Like, there's nothing weird or annoying about this data structure. And that turns out to be really, really convenient, because remember when I mentioned that what I wanted was to expose every single byte type. And if I were to try to do that in Java, the way that you do that is you take that interface, that declaration, and you copy it a gazillion times, and then you manually replace like every single parameter. You change the type to be that one specific type. Or you use like the C preprocessor to manually generate that file for you. I'm not entirely sure which one is worse, but I know that I don't like either of them. Whereas in Clojure, what I did is I wrote a function that takes a vector and returns that same vector, but with a different type annotation. And then I called mapcat over some things, and I was done. And that took like, I don't know, like that function wasn't super easy to write, but whatever. That took like maybe 5 minutes. And most importantly, I don't have a C preprocessor generating Java interfaces. Also ignore error, right? So like when I wanted to attach that ignore error annotation to all of my calls, then if I wanted to do that in Java, then I would have to like copy paste ignore error onto a lot of calls. If I wanted to do that in my Clojure version, then I wrote a function that added the ignore error annotation, and I was done. And another thing, macros, right? So I just mentioned a few examples of very repetitive, annoying code. I have experience binding cryptographic libraries in Python. Let me tell you, that repetition, that is a very, very rife playground for bugs. All sorts of interesting things happen because your eyes glaze over after you see exactly the same lines with these two little tiny differences 500,000 times in the same file. So having a macro that will just elide all of the repetition for you is really convenient and genuinely decreases the defect counts in your software. And then finally, there's the sparkles macro. And the sparkles macro is just a way to generate calls into C. And it will do nice things like, for example, it will add that buffer length automatically. It will look at the signature to figure out if it needs to do that. All of those things are also correctly type hinted, so you don't get like reflection warnings and stuff like that. That was really annoying if I would have to do that manually. Oh yeah, and it also figures out the name of the C symbol to call correctly based on the current namespace. It does a couple of gnarly things, but the bottom line is it saved a whole bunch of time, and it presumably also prevented a whole host of bugs. The only critical thing from just in case anyone wants to know why it's called sparkles, it's because I really don't want anyone to call that macro. That is the opposite of public API. And as I mentioned, this kind of stuff matters. Like that's where real bugs hide, right? And you also get, like in my project, I now have API consistency because I'm lazy. In conclusion, Clojure loves native libraries. And you might not need them. Most projects probably don't. But if you do, don't despair. It's going to be fine. Also, open source is great. So I got JNR for free because some people did some cool stuff. I was able to find at least one bug in JNR. It wasn't game breaking. It was, it was okay. And at least one bug in the Clojure reflector. And also, as a consequence, Python's leading cryptography library now has 0 copy because the author, my friend and former coworker, got really, really jealous because I kept talking to him about how I had @pinned and he didn't. So that was feature development through jealousy. So some future work that I might be interested in is seeing if I can get the same kind of behavior in Clojure scripts. Maybe try mscripting, although generally speaking, I'm a little bit it's not that fundamentally JavaScript crypto is bad. It's just I would prefer to know what you're doing before I accidentally enable that kind of thing. I would like to ship native binaries with Cesium. Right now I don't. Instead, I just give everyone a deb and an RPM that's kind of easy to install. Most of the sysads that I talk to prefer that anyway. And also bind all of libsodium. I just bind the parts that I care about now, which is almost everything that you care about probably too. But there are certainly still things in libsodium that need to be bound. It's not hard. It's just work, and I don't want to do it. If you'd like to talk to me about nonce misuse resistant cryptography, you should absolutely come talk to me about nonce misuse resistant cryptography. If you care about crypto that's easy to use, I will talk your ear off about that. And that's what I'm doing with Cesium. Unfortunately, I have only 40 minutes. And I'd like to end by saying thank you to the conj organizers. I do a decent amount of work. I'm also married to the person who runs PyCon. So I have a decent idea of what it takes to run a conference. This is not easy. Lynn is very good at her job and does an awful lot of work. Wayne and Charles are the people who gave us JNR. They're awesome. And Paul Kerr is the person who got jealous and decided to implement cool features for Python users. And that's all I got. I don't think I have time for questions, but I'll be happy to take them outside. Thank you.